Hey, we are now to Unit 10, which is on quadratic functions. So what we're going to take a look at in this unit is right up here on the screen. You can see the different days. We're looking at about 7 lessons, and we'll get into our review and assessment at the end. Today, our goal specifically with identifying quadratic functions is that I can identify if a function is quadratic, and we're going to look at different forms of functions, whether it's a function as a graph, a function as a table of values, or even a function as an equation. So identify quadratic functions from all those different forms. So let's do a quick review from polynomials from a previous unit. When we were classifying polynomials, one of the ways that we classified them was based on the degree. You might remember the degree was based on the exponent of the variable, the largest exponent of the variable. So for degree 0, that'd be like when we had x to the 0. In other words, there were 0 x's in that polynomial, and we called that a constant polynomial. Constant meaning degree 0. If it was degree 1, that meant that x to the first power was the largest power of x, and those are our linear polynomials. Degree 2, so like x to the second power, or we can say it's x squared, was called quadratic. And that is actually our focus for this lesson, is actually for the whole unit, is quadratic equations, quadratic functions. So we're really focusing in on having that x squared, x to the second power, being the largest power of the variable. So we're not going to see x to the third power, or x to the fourth power, x to the fifth power, or anything bigger than that. It's only going to be, as an equation, something that contains x to the second power in that. So our topic today was identifying quadratic functions, and we're going to take a look at identifying the quadratic function in multiple modes. So when we see an equation, as we just talked about with our review on what does quadratic mean, it means that when you have an equation that's been simplified, it must have the highest degree of 2. And here's an example where we see it's x squared is the term or the part of the equation that has the largest exponent on the variable. So because it's an x squared on the right-hand side here, that means it's a quadratic function, and that's an equation form. All right. Now with graphs, it gives you a certain shape. When we graphed linear equations earlier this year, we graphed lines because linear starts with the word line. But with quadratic equations, the shape that we graph is called a parabola. Okay, parabola, P-A-R-A-B-O-L-A. And the parabola can be one of 2 ways. On the left here, we say this is open down. It opens down because the 2 ends, I call them arms, of the parabola are pointing downward. And that means that they continue to go down forever. Like they never actually stop going down on the coordinate plane like that. Okay, so this is open down. And then on the other side, we have another parabola. It's basically the reverse. It's flipped upward, where now it is open up because the arrows or the arms of the parabola continue in the upward direction. Okay, so opens down is when the arms go down. Opens up is when the arms go up or point upward. So if you see that shape of a parabola, that comes from a quadratic function. Again, that's an equation that has x squared as the largest power of x. Now, tables and ordered pairs are actually very similar in terms of the data that we were given. In a table, it's just a combination of x, y values. Same thing with a set of ordered pairs. So how do we tell if it's quadratic? By looking at just raw numbers, whether they're data in a table or data in the ordered pairs. So what we're looking for is we're looking at the second differences of the y values. Let me explain. I'm going to zoom in here first. So when we're looking at our table of values here, we see our x values are going up by 1s. So 1, 2, 3, 4, 5. And it's important to just notice that because that does make a difference. You have to have that common difference, I guess, on the x values. Now, the y values, however, don't go up by the same amount each time. So if we look specifically at this first group, okay, of y values, it goes from 4 to 9. Now, I can tell that that's going up by 5, but if you have a hard time with that, you just subtract. Do 9 minus 4 to show that it's going up or increasing by 5. Now from 9 to 16, I could count, figure out how much that's increasing, or I can do 16 minus 9 gives me a difference of positive 7. It goes up by 7. 9 plus 7 is 16. Now the next difference, so 16 plus how much would give me 25. I could do 25 minus 16 and find out that that's an increase of 9. And then finally from 25 to 36, looks like I can subtract 35 minus 20, or 36 minus 25 is 11. So that shows an increase of 11. 25 plus 11 is 36. Now what I've just drawn here, those are called first differences because it was the differences in the first y values. Okay. Now for linear functions, we'll have first differences that are the same number. For example, if we have a plus 5 in that first spot, it will always be plus 5, plus 5, plus 5. So obviously this is not a linear function. Now if we look at differences in the first differences, so differences in those values, that would actually be like the second level of differences. We call those second differences. And watch what happens when we look at the differences in the differences. So to go from an increase of 5 to an increase of 7, that was an increase of 2 more, right? Because 5 plus 2 is 7. To go from an increase of 7 to an increase of 9, that's an increase of 2 more again, since 7 plus 2 equals 9. And an increase of 9 to an increase of 11, again, we see an increase of 2 more. So here we have second differences that are the exact same number every time. We call those common second differences. And anytime you have that relationship in your y values, that means that your data, your xy pairs, were from a quadratic function. The same is happening over here in the ordered pairs, where if we look at the x values, we've got 0, 1, 2, and 3. Okay, so they're going up evenly by 1s. So now we're really focusing on those y values. So 1, 2, 5, and 10. And if we want to figure out the differences here, how much are they going up? In the first one, that's going up by 1, since 1 plus 1 is 2. The second group here goes from 2 to 5, so that's plus 3. 2 plus 3 is 5. And the next one, 5 plus what number is 10? Well, that's 5. 5 plus 5 is 10. So my first differences are 1, 3, and 5. So obviously those aren't common. They're not the same. So now we check second differences. To go from 1 to 3, that's an increase of 2, since 1 plus 2 is 3. To go from 3 to 5, it's another increase of 2. So there we have our common second differences that show us that those ordered pairs represent data from quadratic functions. So let's look a little bit more at equations first. So which equations are quadratic functions? Now remember, a quadratic function is a one that has x squared as its largest power of x. So I can see right away that that one has to be a quadratic function because we have the x squared term as the largest power of x. The next example, you know what, that's quadratic also because the term with the largest exponent is x squared. Now in the next one, my next example, I don't see any x squareds. However, I do see parentheses, which kind of tells me this isn't simplified. If I were to multiply this out, it would become negative 5x squared, since we'd multiply times another x there. And then negative 5x plus 1 is negative 5x. So in simplified form, it does contain x squared as its largest power of x. So that one actually is also quadratic. So let's move that one over. Again, that's because of the x squared right there when we were to actually multiply that out. Now in our fourth example, I see x squared as the largest power of x. However, that term, this is actually one term there. We'd have to multiply that out and simplify it to see what it ends up equaling. So that would be what? 6 times 3 is 18. And that would be x to the third power when we multiply that together. So that is not going to be quadratic because it contains x to the third power, which is bigger than x squared. So we're just going to leave that over here. Maybe I'll show that that would have been 18x to the third power. There we go, which is why it's not quadratic. Now, in my final example, we'll move that up a little bit. And this one I see, oh boy, we have 2x minus 5 as one factor and x plus 3 as another factor. Think about what would become the largest power of x if we were to multiply this together. So this is like multiplying polynomials from last unit. Well, 2x times x is 2x squared minus 5x, positive 6x, and minus 15. And I don't really need to figure out what it equals in the end. What I'm more concerned with is the largest power of x is x squared. So that one is also quadratic. So first and foremost, if you see x squared as the largest power of x and the equation's been simplified, that's what makes it a quadratic function. Okay, quadratic, x squared. For graphs are pretty simple. It's just looking at it and finding that parabola. Remember that parabola shape? It's kind of U-shaped. The arms either both go up or both go down. So I see that I have one parabola there and another parabola right there. So the two on my right here are my quadratic functions because I have my parabola shape. This, we're not going to study it this year, but this is actually a cubic function. And then at the bottom, when it's just a line, right, line, that's a linear function, which we studied before. So cubic function would be if it's x to the third power, linear functions if it's just x to the first power. But these are our quadratic functions, our x squareds. And that's what we're going to focus on this unit. All right, last is our data. Okay, and I didn't have any examples for the ordered pairs because I figured, you can take ordered pairs and make a table anyway. So looking at these tables, we're trying to find which one has our common second differences in the y values. So the first thing we notice is our x values here all count by ones. So then when we look at our y values, we're looking for how much change is there from each y value to the next one. So it looks like, and I can just do a subtraction, subtract the second value minus the first value. So 5 minus 4 is positive 1, 8 minus 5 is positive 3, 13 minus 8 is positive 5, and 20 minus 13 is positive 7. So those are my first differences, which I see those are not the same number every time, so it's not a common first difference. Remember, if you have a common first difference, it's linear. But this one, we want to check second differences. Okay, so the differences in these numbers. So 3 minus 1 is positive 2, 5 minus 3 is positive 2, 7 minus 5 is positive 2. There we have our common second differences. So let's take this whole thing and move it over. Let's see if I can do that. There we go. That first one is a quadratic function. Now in our second example, let's look at what we have here. Find the differences in each of the y values. Our x values are going up by 1, so we're okay there. All right, so 4 minus 2 is positive 2. 6 minus 4 is positive 2. 8 minus 6 is positive 2. And 10 minus 8 is positive 2. Since we have first differences that are common, this is going to actually be a linear function. Okay, so the first example we looked at is quadratic because we had common second differences. Makes it quadratic. If it's common first differences, it's a linear function.